In this video, we'll talk about Euler's method, which is one of the most straightforward ways to try to numerically approximate the solution to differential equations. So we have these existence and uniqueness theorems. They basically tell us under certain conditions that we know a solution exists and that there's exactly one solution to these differential equations. However, this fact tells us nothing about how to actually solve them. We have methods for certain types of equations, right? If it's linear, we have a certain method. If it's separable, we can do something else. But the fact that we know the solution's out there doesn't tell us how to find it. There's also, beyond this, many differential equations that we have not seen yet that just there is no direct way to solve them. The main way to sort of get around this when you need these solutions is numerical method. The idea is basically they can approximate a differential equation to get you an approximation to the solution without having to actually work it out by hand to find the actual solution. It's important to realize that for all these methods, we are getting an approximation. Without a lot of extra work, we don't really have a guarantee for how close this is to the actual solution, whether we're going to get similar results to the actual problem we're trying to solve, right? It's always going to be an approximation. The goal is that we can get something that's going to be close enough to be able to model the solution to this equation without having to find the analytical solution as well. And Euler's method provides a good way to do this that does actually satisfy this actual equation here. Now with all this, it's important to also have the existence and uniqueness from before as well. Because if we don't know that there is a solution and that it's unique, there's no point really trying to numerically approximate it. Right? There's no point trying to hunt for a solution if it's not going to be there in the first place. And we'll see this with physical models as well. Even if we have a physical model and we don't have a nice way to sort of guarantee or find the solution analytically, we can guarantee that one exists and it's unique. And once we have that, then we can say, okay, I know there's a solution out there, but I can't find it by hand. Let's run it through a numerical method and use that to approximate from there once we know that the solution is going to be there and there's a point in trying to find it at all. So the standard way of doing this is via Euler's method. So what does the method look like? Well, the idea is basically that I have my first order differential equation written as dy dt equals f of ty. And the idea here is that this, like before, gives me the slope of the tangent line. We know from back in Calc 1 that the tangent line is the best fit linear approximation to the equation. So we can basically, instead of following the actual curve, we can follow the tangent line from some small length. That won't put us on the curve to the solution we're looking for, but it'll put us close to it. It puts us at a new point in the ty plane that will be close to the curve that we're trying to be on. It won't be exact, but it'll be close. We can then take that point and follow the same process over and over again. Take that new point, use that to find the slope of the tangent line, and then step on that slope forward a little bit in time to another point, another t value. And repeat this process over and over again as we go. And this basically allows us to step forward and sort of step forward in time and track along where the solution should go more or less as time goes on. It might not be entirely accurate, but it should be close enough so we can take a small enough distance here with this short distance. What does this method look like? So if I start at some point t0, y0, this will generally be given by the initial condition. I also want to pick a step size h. This will generally be a small number, and for most methods with this, it'll be a constant size h. You can use variable sizes if you want to, but it's easy enough to do with a constant size h here. Whereas we're going to take steps in t of size h and use the differential equation to give us the slope to go from there. What we have from this, then we can find the slope of the tangent line, which is based on the fact that our equation here is y prime is f of ty. I can find that slope just from the value that I start at this point t0, y0. This slope is going to be f of t0, y0. And I want to start at the point t0, y0. I want to step forward in time by a step of size h. And I want to use this slope to tell me where the y is going to be. So from that, we get a new point, t1, which is t0 plus h. So I've stepped h forward in t. And my y1 is going to be y0 plus this slope times h. So forward in t by a factor of h, I've stepped up in y by that slope times h. This gives the next point in this whole process, t1, y1. Now we can repeat this process with this as our starting point to get to a point t2, y2. And then just keep doing this over and over again until we get to the time we want to stop, till we get to a t final or whatever we want to stop this process, then we cut off our process there. And that's the idea of this method. We're just at every point we get to t0, y0, t1, y1, We're going to follow the tangent line for a short distance, pretend that's the actual solution, follow that line, get to a new point, and then reevaluate, change our slope based on the differential equation at that point, and then keep shifting this as we go to follow the curve we want to find for the solution. Again, it's an approximation, but in the right circumstance, that should give us a good approximation to the solution and will give us something reasonable we can use when we're trying to write models about things and trying to sort of model how things behave. We can use these numerical models instead to get an idea of what's going on without having to actually solve the equation out by hand, because sometimes we just can't do that. There's no way to solve it by hand. We need to use these numerical methods to actually get us to these approximations, these answers.